We all have the idea that the atom looks like this, or like that. But the truth is, this picture goes back to what scientists thought 100 years ago, and the structure of the atom is much more complex than that. It went through stages of discovery until we reached the current model of the atom. Later, we were even able to capture an image of the atom. But the question is, how did we take a picture of the atom if it is the smallest thing in this universe? Hello, I'm Briefy. First, I'll take you on a short journey through history. We start in ancient Greece, where some believed that matter was made of only 4 elements: water, earth, fire, and air. They also thought that if we kept dividing matter, we could go on forever. But among them, there were those who believed the atom could be a cube, a pyramid, or a sphere, and its shape would determine its type. The concept of the atom remained mysterious until 1803, when the chemist John Dalton proposed the existence of atoms for a simple reason. Atoms react in fixed ratios. For example, water results from the reaction of 2 hydrogen atoms with 1 oxygen atom. Any chemical compound requires specific numbers of atoms to form. Later, discoveries followed. Electrons, protons, and neutrons were found, and it was shown that electrons orbit the nucleus in certain levels. If an atom loses electrons, it releases energy, and if it gains energy, its electrons jump to higher levels. This is the model we all know about the atom. But unfortunately, this model dates back to 1932. Our understanding of the atom changed after that, with the discovery of quantum mechanics. We learned that electrons are not in fixed orbits, but rather exist as a cloud of probabilities, places where electrons are likely to be found. This image represents the closest thing to the real distribution of electrons around the atom. Each point in this picture shows possible location of an electron. I'll explain quantum mechanics in another episode, but what I want you to know now is that electrons don't have fixed positions, but exist as a probability cloud. The denser the points, the higher the chance of finding the electron there. When we say cloud of probabilities, it's not because we don't know where the electron is, but because it exists across all of those places until we observe it. When we observe it, it takes one specific position. Strange, I know, but that's quantum mechanics. Each layer represents a new energy level. If we go back to the atomic model, you'll notice drawings of orbitals with empty spaces between them. That means there are regions where electrons cannot exist. According to the old model of the atom, those spaces between orbitals were impossible for electrons to occupy. Now, let's return to our main question. How did we photograph the atom? To take a picture of anything, we need light directed at the object, and the reflected light is captured either by a sensor, like in a camera, or through a lens, like in a microscope. For example, if you want to photograph bacteria, you just shine light on them and capture the reflected details. But with atoms, the story is different. The wavelength of visible light is thousands of times larger than the atom itself. Trying to photograph an atom with light is like trying to feel the face of an ant using your fingers. Your fingers are simply too big to get the details. So, what was the solution? One of the most famous solutions appeared in 1981, when scientists built the thinnest needle in the world. At the atomic level, this needle was inert, meaning it didn't react chemically. The idea was to pass the needle over a surface of atoms and measure the repulsion, which gave us an image. It's like running your hand over a surface to feel its details. This technique developed so much that researchers at IBM used it to arrange atoms to form their company's logo, and they even won a Nobel Prize for this achievement. Later, IBM pushed the technique further and created a short video by moving atoms one by one to tell a story. This was amazing, and it showed that atoms are not cubes or pyramids, but spherical, with their size depending on the type of atom. Still, this was not enough to fully understand the atom. Another solution came with the invention of the electron microscope in 1931. Instead of using light, this device shoots electrons, which are much smaller and therefore can describe atoms more precisely. This gave us stunning images of atoms and molecules. Look, even the famous benzene molecule, when imaged, appears with incredible clarity. But we could do even better. In 1999, Ahmed Zewail won the Nobel Prize in Chemistry. What he did was solve most of the drawbacks of traditional electron microscopes. He added special lenses to focus on atoms and introduced a brilliant innovation, accelerating the electrons. In older microscopes, images were taken one by one, with long intervals between each electron pulse, during which atoms could move or change. By accelerating the electrons, the pulses became extremely close together, capturing events at the femtosecond scale, a millionth of a billionth of a second. This allowed scientists to see chemical bonds forming in real time, which greatly advanced our understanding of chemical reactions. Then, in 2012, a team of researchers captured an image of a strontium atom using a regular camera. Wait, didn't we say atoms can't be photographed with light? The truth is, yes, this picture only shows the glow, halo, around the atom, not the atom itself. And since we're talking about atoms, I should explain that 99.999% of the atom is empty space. If the nucleus were the size of a grain of rice, the atom would be the size of a football stadium. This was proven by Rutherford's gold foil experiment, where most of the alpha particles passed through the foil, while only a few were deflected, showing that atoms are mostly empty. But the word empty isn't accurate. It's actually a quantum field, which is why atoms repel each other. In fact, you have never truly touched anything in your life. Because when you think you're touching something, you're really just experiencing the repulsion of atomic fields. And yes, atoms are made of protons and neutrons, but protons and neutrons themselves are made of even smaller particles called quarks, discovered in particle accelerators. In these experiments, atoms are smashed together at unimaginable speeds, creating smaller particles. It turned out that a single proton is made of 3 quarks, but we still don't know what quarks are made of. They might be the smallest things in the universe, or maybe we'll find that they, too, are made of something smaller. What we do know is that atoms have been imaged in dozens of ways, with new tools giving us higher and higher resolution every time. That's it. Thank you for watching this video until the end. I hope you'll subscribe to the channel to support us in continuing. See you in the next episode.